So if you try to make this amorphous silicon cell, the band gap is 1.7, you might be thinking, I'll get a efficiency of 20-30%. On the very best day, on the very first day you test the cell, your efficiencies are like 8 or 9%, because there are so many defects inside this amorphous silicon. So it's an amorphous material, right? So there are so many of these dangling bonds, these tail states. So a lot more of what you absorb, you only collect as current, a very small fraction of that. So the efficiencies of these single junction cells made out of amorphous silicon, they saturate at around 8%. So that prompted people to explore what they can do to improve it. So the idea, which became popular again back in 2007, was to make tandem cells. So amorphous silicon, it has a band gap of 1.7. So let's find a material which has a band gap smaller than this. So you can use silicon germanium. Or the more popular choice is to use this microcrystalline silicon. So this microcrystalline silicon is somewhere close to a polycrystalline. So you have a crystalline material, you have a microcrystalline material, you have a nanocrystalline material, and you have amorphous material. So this microcrystalline material is something which is crystalline but has a grain size of on a micron scale. So it's close to a polycrystalline kind of a material, where the band gap of this is what is that of a single crystalline material. So the band gap is 1.1, but it still has grain and it has defects. So this is the idea which people explored at that time, and you use a thin layer of amorphous silicon to make the top cell. So this will absorb your blue light, and then all the red light and the green light would be absorbed by this microcrystalline silicon. The thing with microcrystalline silicon is, again, it's not a very good absorber of light, just like silicon, so you need much thicker amount of it. So these layers were, the amorphous crystalline part of it was very small, 200, 300 nanometer. The microcrystalline part of it was 2 micron. The other thing about this amorphous silicon or microcrystalline silicon is that you have to deposit it in a high vacuum, or you have to do the CVD of these things in a relatively high vacuum process. So it's not that you can make an ink of amorphous silicon and spray it and make this material. And there's no easy way to do, I should not say easy way, but you have to do this in a relatively high vacuum process, and you have to design these chambers where this material would come in, and the silicon is typically deposited by cracking of this gas silane. So it would take you 30-40 minutes to deposit this couple of micron of silicon on one panel. So that is essentially a big task, and it adds a lot to your adds a lot to your processing cost. But in fact, people were able to get decent efficiency. So if you just look at microcrystalline cell, it gives you efficiency. It maxes out efficiency maxes out at 8.5%. Amorphous silicon, the efficiency again maxes out at 9.5%. For a tandem, using amorphous silicon at the top and then microcrystalline silicon at the bottom, at least in lab, people have showed efficiencies of around 13%. Can you open the door for us? Okay, so where was I? So now suppose you have even made these cells and you have demonstrated let's say efficiencies of 8% in single junction. Now as soon as you place these cells in sunlight, the efficiency starts to degrade, and that has been well known in these amorphous material all the way back in the 70s and 80s. And the reason why this happens is that because these bonds between amorphous material, the silicon-silicon bonds are weak, right? So when you shine a lot of light on these materials, it would generate these electron and hole pairs. And these electron and hole pair, when they recombine, they give away this energy either to a photon or they give it away to the lattice, right? So when they give this energy to the lattice, when they give this energy to this bond essentially breaks, right? So this bond between these two silicon atoms breaks, and it creates these two dangling bonds on each of these silicon atoms. Now, a hydrogen atom can come in and it can passivate one of these dangling bonds, but still at least one of this dangling bond on among these two atoms would be still unpassivated, right? So when you shine light on these materials, you'll just keep on generating more and more dangling bonds. So if you take the cell, you measure its efficiency right when it came out of the lab, it would be something. But if you keep it exposed to sunlight for a couple of hours, it degrades very rapidly, and it degrades very quickly. It can degrade by easily 20 to 30% if you keep it exposed to light. Another thing which is very interesting is that if you take the cell and anneal it, so if you take it and place it in a furnace, then the efficiency goes back up again. And this is very interesting. It's shown in this chart over here. So this cell, let's say you took it and you placed it in Arizona sun, okay, which is as good as placing it in an oven. Right? If you've been to Arizona in summer, it's just like, or South Texas, it's just like being in an oven. Right? So if you look at the efficiency, if you look at during the summer, it goes up, and during the winter, it comes down. Because during the summer, what's happening is that you're annealing the defects in the cell out, because when you keep it exposed to light, then these defects which were formed, essentially these bonds reform and your efficiency goes back up. And so it's very interesting, the temperature dependence of these cells. When you keep it in sunlight and the temperature goes increases, instead of going back, sometimes the efficiency starts to increase, because these bad dangling bonds, they start to passivate when you do that. So now the manufacturing of these cells, as I mentioned, it requires these vacuum process, because you have to do a CVD of your amorphous silicon. And the only way to scale this process is to essentially use these large panels of glass, which are, I remember we used to sell a line which used to do process on these glass, which was 5.6 meters square, and that's much taller than me. And there would be these chambers, so just to depict the height or the might of these chambers, these are two people who are standing next to it, right? So this chamber is big enough such that I've been in one of these, so you can stand inside one of these, and you can have a barbecue party inside. It's that big of a chamber, and you have 6 of them or multiple of them connected in a cluster. Since you want to scale this process, right? Each of these steps would take 30-40 minutes. So the only way you can scale is that use these large panels and use these large reactors to deposit this amorphous silicon. So we used to sell these lines which were costing a lot of money to essentially, it was a turnkey line. Turnkey line is if you want to sell solar to somebody who does not know anything about solar, you sell him a turnkey line, which means you come and turn a key and the glass goes in one side and the panel comes out on the other side. So a turnkey line, if you buy it of amorphous silicon, it would set you back by quite a lot of money. And I've posted a video of how this line works on the class website. Now, okay, let me discuss the topic that I'm really very excited about. At least it floats my boat. At least I get very excited talking about it. That's organic photovoltaics. So if you look at the organic cells, they are indicated in this orange color over here, and they lie at the very bottom of this pyramid. Right? Their efficiencies are the lowest, and there's always said the fortune is always at the bottom of the pyramid, and at least there's some reason to think like that in this case. And the reason is that the efficiency, even though they are low, if you look at how they have been rising very quickly over the last few years. And every 6 months, I see a new paper which claims a new record efficiency of these cells. And as people are starting to look into it more and more, it's starting to progress even more rapidly. Earlier, it was mostly in the domain of universities, which were reporting these efficiency. Nowadays, there are companies. So Konarka is a Massachusetts-based company. This Helitech is a German-based company. So there's some industrial interest in these field as well. For example, especially this Sumitomo is a chemical company, is another chemical company. So chemical companies obviously have vested interest in promoting these organic cells, because these are the same chemicals they sell for making other plastics and so on. So they would of course like to see other application of these chemicals for making solar cells. Okay, the other thing which is that it can enable really new form factors, and to show that, let me try to show you a video. And let's see if I can. Turn up a button.
Manufacturing scale-up operation. The facility was originally forward corporation before the facility. Some of its primary photographic products. The facility is 250,000 square feet. About half of that is the manufacturing space. Another 25 or 30% of that is warehousing. There are a lot of technologies in the world that don't look at.
Actually, sorry, this is not the.
It requires very.
Konarka is a Lowell-based company who is taking a new approach to the traditional solar panel. Surprisingly, it adapts a familiar and time-tested technique.
We've created a polymer photovoltaic paint. We're applying the material very much the same way that a traditional printing press applies ink to a substrate. They're dry, just like inks are dried in a magazine press. So it's very traditional in terms of the materials as well as the technologies that have been with us for many, many years.
Using a modified printing press, Konarka creates a flexible solar panel called power plastic.
We start with a mylar plastic film, and we coat several layers of material on that mylar, including a silver backplane. Once this panel is completed, bus wires, which are actually electrical conductor wires, are put down on each side of the panel, and then it's sealed again on both the front and back plastic.
Konarka's power plastic is a thin material that conducts electricity in a number of different environments not normally associated with solar power.
And you can see that, but there's a small voltage registering that this piece of material is bringing power. I move it over to the window, it will actually jump out. But by putting it on surfaces and allowing people to use this material, you don't have to think anymore about, gee, I need to charge this because I have to by getting close to the sun. Even if the material is put at a vertical angle, it's still collecting photons from as high as 70 degrees off of the perpendicular to the surface, which for many, many applications where solar was never able to be used, now we can start using it on
While creating products that generate solar power, Konarka also looks at its environmental impact from manufacturing to the end of the panel's life.
Everything about this material is recyclable, from the plastic films that we use to the silver inks on the back. This can be electrolysis process for you and reclaim. There are companies that actually do that in the electronics industry.
Kanarka is envisioning a world where through partnerships with other companies, they can bring power anywhere.
We have folks doing products like this. Products from companies called Moon Solar. Moon is put a panel of our material in the back, and if that panel's tied to a small battery,
If you go to an airport, you can you get a lot of these bags which have solar panels on them.
Carry a cell phone or an iPod and be able to charge that anytime and any place.
A simple act of stopping for a cup of coffee could recharge in more than one way. This vision has been realized by a company called Sky Shades.
What we've just announced with them is what they call Power Umbrella, which is a product that uses 16 of these 7-8 watt panels to collect energy into a bank of batteries. That those batteries then provide laptop power, cell phone power, lighting power, so that evening and lighting under the umbrella, it was all created by power from the sun.
Taking Kanarka's process to the next level, power plastic can be modified to give windows a power punch.
What we have is both a transparent electrode on one of the surfaces on the front, and on the back a screen printed silver electrode. So both energy coming.
It looks red in color, right? If you look at it, you can see why that.
As Kanarka looks further into the future, new applications for their technology are becoming possible. At an early stage of development is a product called Power Fiber, which removes the panel from solar collection. Instead, they have created a special thread which can be woven and connected to form a new kind of power grid.
So you can imagine, I don't have to wear solar panels on my jacket. I could actually have the jacket itself host power. There's quite a lot of exciting things that come from the wearables side of the world, from electronics to medical devices to military devices, sensors that collect data about the environment, and on and on and on. So we will develop that next week. Keep saying time.
Right, so you get the idea. So there, one thing you notice was that it's exactly different kind of form factor, right? Once you put it on a flexible piece of plastic, aluminum is still flexible, but it's not. I mean, it can enable form factor like shingles, so you can bend it, make tile out of it. But if you put it on a piece of plastic, then you can enable a lot of other form factors which were never possible, right? So that's something we saw in this video. And so, let's discuss some of the things we saw in this video, and I'll try to explain why that was the case. For example, why were they looking red and not blue and stuff. So one thing that you need to, and that's again something that gets me really excited, is that to understand these organic photovoltaic cell, you need to understand this idea of Exciton. So far I've been telling you that whenever you have light shining on your cell, you generate an electron and hole. The electron goes one way, the hole goes the other way, right? And you guys always, you never know, one of you complained that you always, you believed in what I said. But now look at it in perspective of a hydrogen atom, right? So if I have a hydrogen atom and if I shine light on it, right, it generates this electron, but it goes from one shell to another, right? It does not go away from your nucleus. It's essentially contained in that nucleus. So why does, in a semiconductor such as silicon, when you shine light, you generate this electron and hole, but they start to go in opposite direction, right? So versus if you have just say one atom, it stays connected to that atom, right? That it just jumps to another orbit. So one can argue that you can argue that okay, that is related to this thing we studied in our high school chemistry, that this is a Bohr model of my atom, and my energy in this different shell is given by this formula, where it's inversely proportional to the square of the dielectric constant, and it's also proportional to the effective mass. So for a semiconductor such as silicon, you have low effective mass and you have high dielectric constant. Especially you have the dielectric constant of silicon, for example, or most of the semiconductors, between 13 to 15. So that makes this energy of this Bohr atom very low. So for this silicon, this comes out to be 13.6 milli electron volt. And you can say this is very less than even the the free energy that you have available at room temperature. So you have 3 kT, that itself would be 75 MeV. So I can easily thermalize these things, and they will separate into electron and hole pairs. And these electron and hole pairs can essentially, they can flow in different directions. Okay, so this is the reason why we always treated them that if you generate an electron and hole, you can collect one easily at one contact, and you can collect the other one at the other contact. But this is only true for these semiconductors. If I consider the case of my organic material, so they have a K value of only 3. Okay, so most of your organic, they're almost they have very low K value. So now if I calculate this same Bohr energy, it comes out to be 150 MeV. And this is not an easy thing to overcome, right? Your the amount of energy you have at room temperature just by thermalization is not efficient to overcome this 151 MeV, right? So instead of producing these electron and hole pairs, which you could easily separate, it would generate these excitons, which is basically one electron and one hole, which are they're closely bound to each other. And if you look from far away, they essentially look neutral because there's a positive charge, there's a negative charge, right? So overall, since they are bound to each other by this energy, they essentially are charge neutral, right? So now how do I separate them? So you might think, okay, let's apply electric field just like we did in a solar cell. So let's apply electric field. My band diagram will become something like this. My holes will go down the hill, my holes will go up the hill, electrons will go down the hill, right? So people have tried that with no success, right? Because these things are bound to each other, so you need a very high electric field to separate them out. Right? So these excitons, the electron is bound to the hole, so you can't separate them out in a normal p-n junction the way which we are used to thinking, or even using selective contacts, right? So how do I generate this very high electric field which has enough energy to separate out these excitons, right? So one way to do that is essentially use a heterostructure, right?